Hello everyone, and welcome to our third and final part of the review for this AIME I from 2025. We're going to go through questions 11 through 15, which, as in the thumbnail, I've said that they are tough to solve and easy to mess up. I mean, you can see that this question literally already takes up our entire screen, so that is not a good sign in terms, not of difficulty, but in terms of all the different ways in which stuff can go wrong. So as we go through these final 5 problems, I'm not going to focus on the calculations as much, otherwise this video will get exceedingly long and boring. But I will focus on the places in which we can go wrong. So also do pay attention. If I say anything wrong, it could either be that I've actually messed up, or it could be that I am just going to see if you are attentive enough, because such a mistake could also happen to you. If you look at the lengths of our first 2 videos, you would see that added up to the runtime of this video, it does fit within 3 hours, but it's still not easy to solve them. There will be a lot more dead time in reality. So that's where the challenge of the AIME is. We are not in a huge hurry. If we want to do 10 questions, it's more of can you solve them. But if you want to go beyond that, we are now in a hurry because there will be time you need to just spend thinking about things. Okay, so now let's look at question number 11 here. We have to find a way of ignoring some parts of the question. So the description of this piecewise linear function, this sawtooth pattern, I think is quite easy to understand. The graph, in fact, is self-explanatory. So let's just push that aside. I am interested in a parabola that intersects this graph. This parabola is x is 34y squared, which it's not y equals to 34x squared, it's x is 34y squared. So it would actually go down, let's say, this side. And therefore, I could essentially ignore the negative portion of this graph. So let's do that and save a little bit of space. I'm also told that the sum of the y coordinates looks like this, where a, b, c, d are positive integers. Now, I will bear that in mind that in a way, this is neither very ugly nor very nice. Right? So it doesn't just all cancel out to give you like a rational number, but it does not have also a huge stack of square roots. So I'm expecting a bit of an efficient approach to exist, but not one where everything cancels out. Okay, so now let's think about how we're going to do this. Essentially, this graph here, what I know is that there will be different pieces of it. It's a piecewise function. It's different pieces where each piece is actually going to have its own function. So this first piece is y equals to x. Then the next piece downwards is 2 minus x. That's given in the question above. And then it just continues to repeat. This is y equals to x minus 4. This is y equals to 6 minus x, and so on. Now, since the parabola that I'm interested in is x equals to 34y squared, I know that it means that my x only reaches 34 since y only goes between -1 and 1. So this is not going to go on forever. I need to care about the equations. Y equals to x. In fact, let's not write y equals to x. Let's make x the subject. X equals to y. X equals to 2 minus y. X equals to y plus 4. X equals to 6 minus y, and so on. These ones correspond to the intervals as in the question, -1 to 1, 1 to 3, 3 to 5, and so on. Let's just write the and so on. It goes up to the place where the bottom row is 1 mod 4 to 3 mod 4. So 33 to 35 should be the end of it, and that will be x equals to 34 minus y. I think that should be as far as I need to care about. This is going to be still needed, and then this one, I'm not sure. We will see. Now I want the sum of the y coordinates, and I realized that substituting in gives me quadratics. And I know that from quadratics, I can use Vietas. So the interesting thing about all of these is that all of these in the top row will look like 34y squared minus y minus something equals to 0. And so Vietas would tell me that the sum of roots is just 1 over 34. I mean, for each of the lines, the sum of the two solutions would look like that. The same thing happens for each of these except that it would be plus. So the sum is negative 1 over 34. So you can understand straight away why most of it is going to be cancelled off. I just need to be careful of the boundaries. For everything starting from here and ending here, I know that the two solutions, both graphically and algebraically, it makes sense that they are between -1 and 1 for y. For the x equals to y, 34y squared equals to y, that is okay. You get y is 0 or y is 1 over 34. Be very careful because when you draw it, it may look as if there is no second intersection with the line y equals to x. So you might think the only solution is 0, but we should still check that one algebraically to be sure. And yeah, there is a y equals to 1 over 34, which graphically would be quite imperceptible. For the last one, I will also check that. I think I need to check the quadratic formula. There's no way around it. So you get y equals to -1 plus minus 1 plus 4 times 34 squared over 2 times 34. This is interesting. This is interesting because I can tell that the 4 times 34 squared is plus 1. So this square root is 2 times 34 and a bit. And if it's 2 times 34 and a bit, if you took -1 minus that over 2 times 34, you will end up with something that is a bit less than -1, which is out of the range, meaning the intersection would actually have been outside of the range of the line. It would have already turned around. So that means that the only leftover solution would come from the plus. Now is the time to calculate it, and this part I will just fast forward the calculation for you. So this is the one solution that you keep. We know that everything else, the 1 over 34 and -1 over 34, we are going to cancel them off, except for this 1 over 34 here at the end, which doesn't cancel with this since we only got half of that sum, or rather one side of that sum. Okay, and so therefore the answer you get is 1 over 34 plus this, just switches this to a plus. And I suppose it's a bit of a nice thing that the question has said that it's in this form where a, b, c, d are positive integers. So that reduces the likelihood that we would have just forgotten and left this as -1. Now we know that it does look like this, and summing up all those four values gives you 259 as our answer. For this kind of question, I would definitely redo the calculations and reread it again to make sure I didn't mess up anyway. It is almost like your senses tell you that, okay, there's a lot of ways that I can make mistakes on the boundaries in terms of calculations. So identify the places where you can go wrong, even as you're trying to figure out the big picture solution to the problem. Okay, number 12. Yet another one that is a little bit frustrating. A little bit frustrating because we are given a 3D geometry setup and a plane which x plus y plus z is 75 is quite impossible to visualize that well. But even if you can visualize it, I'm then told that the coordinates satisfying these inequalities form three disjoint convex regions. I just have to solve it, right? I have no choice. So I think I'm just going to solve it. I will be quite careful in the way that I do it, and then we'll see how that translates to three regions. A chain of inequalities, I will just do them two at a time. So let's just see what we get. Okay, I'll move everything over to the left side. I can see that it is factorizable by grouping. And so the second one, because it's just cycling the variables, I'm not surprised. X became Y, Y became Z, and Z became X. So you would end up with the same thing with the variable cycle. Okay, so I need both of these to be true. Now, this inequalities would give us two cases. 2 times 2 is 4 cases, and I expect 3 regions. So I'm not going to look for something that is a whole lot better than this, so to speak. I am completely willing to accept if it turns out that this is the best I can do. And I expect that if there's 4 cases, one of them is going to fail for some reason. And then the one that fails, it will tell me something. Okay, so x minus y, 1 plus z is less than 0. I will just write each of these down. Actually, so let's say that I go plus minus plus minus. So if I have this, it means that x bigger than y bigger than z. And also that my x and z are both less than negative 1. Now this looks immediately wrong. This looks wrong because if by numbers are all less than negative 1, they cannot sum up to 75. So meaning that this does not appear on that plane with x plus y plus z is 75. Okay, so good news is that we have found a case that doesn't work. Now, bad news is that most likely the other 3 cases will all work. Question is asking me about the one with finite area. So I don't think it's hard to tell which one has finite area, but we will see. Okay, so next one is if the signs go plus, minus, minus, plus. Now, plus, minus, minus, plus means that y is the smallest one. It means that we are told here that x is more than minus 1 and z is less than minus 1. So I guess that should be actually chained up like this, right? That would cover everything. Okay, so that covers everything. Now, is this possible? Uh, I guess the answer is that sure, it's possible, but finite area means that your x, y, and z cannot be unbounded, right? And I can see that, well, my x and my y, they can move in opposite directions. I can make x very big and y very small. So since that can happen, there is no way that my region has finite area. So I can also exclude this case. Okay, let's go for minus, plus, plus, minus. This is essentially the reverse of the previous one. Now instead, y is the biggest. And you would see that by the same logic, I can make y increase and x decrease. And doing so is going to give me, again, x and y are unbounded. The region would be infinite. So unfortunately for us, it seems that we guessed poorly. We have to go to the fourth and final case. Legitimately, I wasn't sure. I wasn't trying to script the video that I will go through all the cases and leave you with the last one. I actually just am unfortunate because sequentially minus plus being the last one is kind of expected. So, okay, let's see what we get. X minus y, y minus z are negative. So it's actually going to be x less than y less than z. And both x and z are more than negative 1. Okay, so that makes sense because x plus y plus z is supposed to be 75. It makes sense if they are in this order and all of them are more than minus 1. So what this basically tells me is that the boundaries are made up of 3 inequality signs. Now, each inequality sign is corresponding to one side of a line on a plane. If you have 3 lines, that's a triangle. And I'm happy if it's a triangle because I can get the area quite easily. Okay, so here's what I'll do. I will just put negative 1 equals to x, x equals to y, and y equals to z as my 3 equations. I also have the x plus y plus z equals to 75 as my ambient equation. Okay, now I'm going to just take them 2 at a time. And get the points where they lie on. So they're both negative 1, this would be 77. If x, y, z are all the same, that would be 25, 25, 25. And if I have got the first and third, then that would be negative 1 for x and 38 for the other two. Great, so these are 3 points. The reason why I'm doing it like this is that in 3D Geom, it's pretty difficult to do a lot of these calculations without vectors, and I don't want to assume that. But if you know all the distances, all the lengths everywhere, you often are able to just, say that, treat it as a 2D geom question. So with all the distances available to us, I can easily find this area. Okay, now I will just pause for a second because my Microsoft Word is lagging a lot. By the magic of editing, you just see it as a few seconds, but let me edit it afterwards. Let me just pause to address the lag issue for a second. Okay, so I think that yeah, the lag issue seems to be resolved now. So we can finish off this calculation for the area. Um, just distance formula. And conveniently enough, you notice that all of these distances are pretty nice. So if they were just a bunch of random things, I would be quite prepared to either do a cosine rule or use a Heron's formula. But I can see that factoring out 13 square root 2, one of them will give me 3, one of them will give me root 3, and one of them would give me 2 root 3. If I take out a further square root 3, then I get a nice surprise, which is that this is actually 1 root 3 2 right triangle. So much to my pleasure, it means that the area, this is the scale factor, so square this, and then root 3 over 2 is the area of that 1 root 3 2 triangle. Okay, so area is 507 root 3. Question asked me for a plus b. Okay, so answer is 510. On to question 13. Alex divides a disk into 4 quadrants with 2 perpendicular diameters intersecting at the center of the disk. He draw 25 more line segments. Oops, I'm quite sure this is my typo, not the AIME problem typo. 25 more line segments through the disk, drawing each segment by selecting 2 points at random on the perimeter of the disk in different quadrants and connecting these 2 points. Okay. So we start off basically with a disk divided into 4 quarters. And then after that, we are drawing 25 random chords with the condition the chords have endpoints in the different quadrants. Okay, so that's quite interesting. I need to decide on this expected value. How am I going to count it? The reason why I want to know how to count it, and I said not calculate the expected value, just count the number of regions, is that linearity of expectation will allow me to handle them separately. So for example, I could say that, well, I could just consider the expected number of new regions that are formed by each line. But that is going to be very clumsy, mainly because each of the lines, the number of new regions is not going to be independent of the previous ones, and it's not independent in a way that is quite hard to compute. So I can't do it that way. The way in which I would do it instead is our very famous Euler's formula, which applies both to polyhedra as well as to planar graphs. Now, the formula is v minus e plus f equals to 2, where v, e, and f are vertices, edges, and faces, or regions. But because the 2 would include the infinite outer region, which I'm not interested in. I am interested in how many it divides the disk into, so I'm just going to change this to 1. Then that will basically tell me that this is the thing that I will use to compute the number of regions, which is the number of faces. I just need to get the expected number of vertices and edges. Sounds simple, right? But hang on a second. vertices are not just going to be the endpoints. Now, this Euler's formula applies to planar graphs, meaning things that you can draw with no intersections of edges, meaning that if you want to say this has no intersections, you have to count this as a vertex as well. So for instance, here in this starting point, there will be 5 vertices, there would be 8 edges, including these arcs are also edges, and 4 faces, which is how you get 1. So what I'm saying is that I'm now going to have to figure out what's the expected number of vertices, which is made up of both the endpoints and the intersections. Right, 27 times 2 plus number of intersections is the number of vertices. Now, for the number of edges, I also can say that it depends on the number of intersections. The 54 will be the starting point, which is the arcs around the circle. If there were no intersections, then you would have 27 segments. And then after that, you have got the intersections. Each time when there's an intersection, it actually splits 2 lines into 2. So it's plus 2 times the number of intersections. Take note that the number of intersections that I am referring to is intersections inside the disk. I am not counting the vertices themselves on the perimeter of the disk as being intersections. Okay, so now that we understand that, substituting it in, you are going to get it is 28 plus the number of intersections. And so I just need to find the expected number of intersections and add 28 to that. Okay, so this is where graph theory ends and probability starts. Now there are 2 diameters and the diameters are fixed. 25 random lines, random chords. So I need to also split up when I said expected number of intersections. Is basically from each pair, do they intersect or not? So the expected number of intersections is basically the sum over all pairs of lines of the probability that the lines intersect. I mean, they are not going to be just multiplied by 27 choose 2 because diameters and random chords don't behave the same way. So first of all, the diameters have 1 intersection, that is the center, so guaranteed you have 1. Okay, so diameter and a chord. The chance that I have a chord intersecting with the diameter, if you imagine I focus on this chord, I pick a random vertex in the first quadrant as without log being the first endpoint. Then the second endpoint comes from these 3 quadrants, and for 2 of those quadrants, it will intersect the diameter, for 1 it will not. So it's a 2/3 chance. Then you have 2 chords, which is obviously the most tricky one. Now for 2 chords, you can basically think of it as I further split into cases of whether the endpoints are in the same 2 quadrants. Okay, so this is more casework. We need to be very careful. But we cannot sort of just say pick a random one here and then find the probability, because that's pretty complicated, right? And we do not want double integrals for sure. So it is a lot easier to just say that, all right, if my two chords both have the same two quadrants, that happens every 1 in 4 choose 2. Now, if they are in the same two quadrants, let's say that they are the same two quadrants here, then there's a half chance that they would intersect. Basically, the two configurations, which is that, is it like this or is it like this? There's a half chance because you can treat it as you pick these 4 points first before you then draw the chords. So there are two ways to draw the chords. One works, one doesn't work. So this case is 1/2. The next case is that the 4 endpoints are in 4 different quadrants. Once again, this also has a 1/6 chance of happening, because if your first chord uses 2 quadrants, the second chord has 1 pair out of 4 choose 2 pairs of quadrants that could have been chosen. Now, if they are in 4 different quadrants, this actually amounts to pretty much the same thing as the case where they are in the same 2 quadrants. It will still be a 1/2 chance. No, sorry, no, it's not the same, right? It's not the same, yes. It's not the same because actually if you just have the quadrants, that it only depends on the choice of quadrants, right? And so if let's say that the first one look like that, definitely no intersection. If the first one look like that, there's definitely an intersection. The first one look like that, definitely no intersection. So sorry, it's that one's not half. That one will be 1/3 because the position within the quadrant doesn't matter. So this is different. Okay, now this one is the one that has one common quadrant. 2/3 because it's just 1 minus 1/6 minus 1/6, but you can check that there's a 2/3 chance that they have one in common exactly. If they have one in common exactly, then the same thing happens again, which is that let's say that now these are the two different quadrant starting points, but they both end in the same quadrant like this. Then there's two possibilities, one yes, one no, and so this one is also going to be half. Okay, let's add this up. We get a total of 17/36, if I'm not wrong. So let's put it together. If I am correct, great. If I am wrong, let's hope I get a non-integer answer so that I know that I'm wrong. Okay, so the expected number of intersections, 1 for the two diameters. 2/3 times 2 times 25. 17/36 times 25 choose 2. Let's see whether this works out. Okay, there will be a 3 below, so it would be 425 plus 100 is 525 over 3 is 175. Great, so this is actually integer, so I think I've not messed up. 176 is not your answer. Don't forget to add 28 at the end. So 204 is our answer. Question 14. Now, incidentally, if you're looking at these last few questions, part of the challenge of the AIME is that they are trying to make the time feel justifiable. So it is not like an AMC. The questions have to take longer, but you still don't get partial credit, unlike, let's say, a USAMO or our SMO round 2. So be extra careful for such problems, double check, triple check. It's pretty painful if out of everything, one calculation is wrong. Okay. Question 14. You have this convex pentagon with AB is 14, BC is 7, CD is 24, DE is 13, EA is 26, and angle B equals to angle E equals to 60 degrees. Okay, let's just try to draw it. So AB is 14. BC is 7. That's interesting. I'm trying to draw it in order. There is a 60 degree here. So in fact, there seems to already be a 30, 60, 90 triangle that is in there. Okay, a bit of a tip for drawing diagrams is that as you draw, try to make observations while you're in the midst of drawing, right? Don't, unless it's a question where clearly you need to draw everything before you know what's going on. If not, like, as you draw each line, just pause for like 3 seconds just to say, anything interesting here? Otherwise, there is a good chance that you will miss out the property and then it's very hard to find it back. So because this is 1:2, right, and 60 degrees, I recognize this as a 30, 60, 90 triangle. And in fact, I can see already that there is a 13 and 26. So the same thing happens again at E. Right? Okay, this should be a lot bigger actually. I'm not sure whether that matters, but let's draw it to be a bit bigger than that 14, right? 26 should be a lot more than 14, so. There's no spiral similarity here. But I do realize that it's essentially these two right-angled triangles, and then you pivot them until CD is exactly 24. So in a way, everything is fixed. Right? The whole diagram is actually up to like rotations and reflections of the whole thing. It's a fixed pentagon. Now, we know congruent triangle conditions. We don't know congruent pentagon conditions. So we do need to take a second to think, do I actually get to choose A, B, C, D, E? But I basically do not. Okay, let's just write down before I forget. I know these values are like this. Is there anything special about 13 root 3, 7 root 3, and 24? I don't think so. I mean, it's not going to have another surprise right angle triangle there. 24 is the longest side of this by a little bit. And that's about all I can say for now. Right? 13 root 3 being quite close to 24 is actually correct. So, okay, so I think we'll just leave this as it is. And now we'll deal with x. We are trying to find the least possible value of fx, where fx is ax plus bx plus cx plus dx plus ex. Okay, normally, if let's say that it were a few of these, I would think of a triangle inequality, but there are 5 things here, so I cannot imagine any good reason why the triangle inequality of log x is just going to be this point or that point is going to work. So that's a bit tricky. I also cannot imagine using quad geom on all of this or trigo on all of this blindly, because that is going to be quite horrendous. Okay. Now, what I do know is that I could find most of the lengths if I needed to, right? So like, for example, this is 30 degrees and 30 degrees, so I can find this angle, uh, and if can find that angle, let's just see what it is. Is there anything else nice? Okay, this is going to be uh, 169 times 3, 547, 147, 576 over 91 times 6, 546. Oh, that's interesting. Uh, it's just 1 over 7. Okay, that's quite nice. Uh, of course, that isn't a special angle, but it does mean that doing calculations might not be so bad. Okay, uh, so that means I could find all kinds of other lengths if I wanted to. For example, I could find CE, I could find BD, I could find BE. Uh, let's just pause for a second and think of how am I going to relate it to AX, BX, CX, DX, and EX. Now, there's something that we don't often use, which I think can make sense here, which is our Ptolemy's inequality. Now, Ptolemy's inequality is just the inequality form of your Ptolemy's theorem, where instead of it being equals, it's just the sum of the products of the opposite sides is greater than the sum of products of the diagonals if it is not going to be cyclic quadrilateral or collinear points, neither of which um, actually, well, I mean, I can't make X collinear with everything, but maybe I can make X concyclic with some of them. There is a pair of 90 degrees, pair of 30, and pair of 60 degrees, so maybe that's a way to do it in a way that is concyclic. So that's an interesting potential there. I'll put X somewhere that maybe makes something cyclic, since I can't really make, or maybe I can make two lines collinear. I mean, like maybe X is the intersection of two lines. I'm not sure yet. So anyway, let's just try to make Ptolemy's inequality tell us something about these. I want to work with stuff that let's just put X somewhere in the middle, like let's say here or something. It looks like it should be somewhere in the middle, right? Intuitively speaking. Let's try to use Ptolemy's inequality, let's say on just ABCX. So in other words, on the 30, 60, 90 triangle and X, because I know that factors will disappear quite nicely, right? So that seems to be a good idea. Okay, so AB times CX plus BC times AX is bigger than AC times BX, or rather bigger than or equal to. The 30, 60, 90 would make it such that 2CX plus AX is bigger than root 3 BX. Okay, and so likewise, I suppose if I were to repeat the same thing on AEDX, the 2DX plus AX again is bigger than or equals to root 3 EX. So interesting. Interesting because they are quite similar to each other. I definitely cannot use this in order to make all of these equal, but I suspect something nicer is going on here because normally these kinds of things, the point that makes it work for, let's say, a pentagon would just be some horrible mess of algebra. There's no usual way of doing this well. So I suspect that there's more nice features to come. And so I dare to just, since there's A, C, and D, and if I just add this, I will get 2AX, 2CX, and 2DX. Let's add them. If we sum them, and why not? Let's just put 2BX and 2EX on the left side also. So that would give me the f of x which I wanted. And then it will become 2 plus root 3 bx plus ex. I feel very tempted to say that this can then be just the triangle inequality. But that requires a lot of things to happen at the same time. So it requires that equality 1, x is on BE. 2, ABCX is either collinear or concyclic, and obviously they cannot be collinear. And I also need AEDX to be concyclic. Okay, so let's look at that. ABCX is concyclic. Well, it has to be on BE, right? So let's start with drawing it on BE. Now, how can, let's say, this be concyclic? Oh, this 90 degrees needs to come here. And that will actually work with this. Okay, great. So it turns out that the two circles do really intersect down there because, yeah, it is true that if you were to draw the circle, we know AB is the diameter here, AE is the diameter here. Yeah, it makes sense actually that your two circles would intersect nicely like that. So great, we have found x. And not only have we found x, we have found x just geometrically, but I don't need to go and describe x much more. I just need to say that my answer will just be 2 plus root 3 over 2 multiplied by the length of BE. BE can be obtained by the cosine rule, since I have already got that cosine A is 1/7 just now. So I know that I can just have BE squared, 24 squared, 26 squared, and then this is cosine of A plus 60 degrees, where the cosine of A is 1/7. Okay, so let's just fast forward this calculation because I did this in advance to make sure it works. So it turns out that this is really 1444, which is 38 squared once you use your cosine identity. And this would be 38 plus 19 root 3, giving our answer as 60. So this is pretty neat. I would say that it's a bit too good to be true, yes. So if the question you're going to ask is, how did I know that this is going to work? I can only solve a question like this with the assumption that it's an AIME question. It should be reasonable enough that something good happens. It cannot just be asking me to have the sum of 5 square roots, 2 variables, and then somehow it simplifies. Right? That feels like it is not very reasonable. Okay, last one is question number 15. This is a very straightforward statement. It's just asking you for how many ordered triples or A, B, C less than or equals to 3 to the 6 are there, such that the sum of cubes is a multiple of 3 to the 7. And then because it is not surprising that this number may be very big, I need to find it mod 1000. Okay, there's actually quite a lot of number theory that we can say here, and some of it may turn out to be useful, some of it may turn out to be not useful. But the first thing that I will be reminded of when I see this is, why are we stopping at 3 to the 6 for 3 to the 7? And then I remember that the common explanation I have for why is it that cubes are only 0, 1 or -1 mod 9. How come so nice? It is so nice because actually when you have this tree there, you don't need to go through a cycle of 9 for 3 steps later. Sorry, this is 27. You already end up repeating, mainly because of the trees doubling up there. So I suspect that maybe 3 to the 6 in a sense is already a complete cycle. Let me just confirm that if I were to shift it forward by 3 to the power of 6, does it change anything? Yeah, definitely this is fine. Okay, so it means that in reality I am it's no difference from if, let's say, instead of it being 1 to 3 to the 6, you changed it to 1 to 3 to the 7. It's the same, except that it would have now multiplied the number of triples by 3 cubed, which is probably why it's chosen this way. So I understand that. Let's see also, so from here, I said that 0, 1 and -1 mod 9. They're all different when I take, let's say, the first 3 cubes mod 9. Now, are all of these going to be different mod 3 to the power of 7? Is that the reason why it's like this? Now, clearly the answer is not exactly, right? Because if, let's say that I have just 3 to the 5 cubed, 3 to the 4 cubed, 3 cubed, those are all going to be 0. But if we ignore those that are multiples of 3, are they all different? So let's check. So if these are not 0 mod 3, and if I confine them to this range, what does do they clash? Basically, what does x cubed congruent to y cubed say? Is the same thing, right? So if I can find a contradiction, then I know that they don't clash. If I do not find a contradiction, then great. Well, I can argue this using either LTE or primitive roots. I think I'll go with LTE. If 3 to the 7 divides x cubed minus y cubed, I know that from LTE, the number of 3's in here, you can lift the exponent. Literally, that's what LTE is, right? So lift the exponent. This is 1. This is at most going to be, well, this is not at most, this is less than 6. Unless x equals to y. Okay, so that confirms that all of the cubes will be different. So this range of 1 to 3 to the power of 6, you can think of it this way, that when you take your numbers from 1 cubed, 2 cubed, 3 cubed until 3 to the 6 cubed, there are the multiples of 3 that you are going to just toss out first, but you will end up with all possible cubes are going to be different for the rest. So all of these cubes are different, uh, and there will be a total of, this is 2/3 of them. So it's 2 times 3 to the power of 5 distinct cubes here. Mod 3 to the power of 7. This is 2 over 9 of the residues mod 3 to the 7. And conveniently, I realized that, oh, that means that because I already know there are 1 and minus 1 mod 9, that's also 2 out of 9. So it means that all of these are going to be 1 and minus 1 mod 9. They are basically going to be 1 and 8, 10 and 17, 19 and 20, all the way down. These are what they are. So these are all the cubes down there from the not multiples of 3. Now let's go back to the remaining ones. All of these are multiples of 3. I can factor out a 3 cubed from them. And this is what you're left with. Now, by the same logic, we can again split off the ones that are not multiples of 3. And then, of course, on the other side, you have those that are multiples of 3. And if you factor it one more time, it will shrink down like this. Okay, so I have divided it into these 3 portions. The ones on the left here, 3 to the 6 already as a factor, and it's mod 3 to the 7, means that you only care about the things inside mod 3, and the things inside mod 3 can be anything. Right? It will just go 1 minus 1, 0, 1 minus 1, 0. And so the implication is that this would be just 3 to the 6, 2 times 3 to the 6, and 0. Each of them appear 3 cubed times each. for this one, have got 3 cubed here, so I only care about this part, mod 3 to the power of 4. Now, by the same logic, here I said by the time I reach 3 to the 6, I've actually covered all the things mod 3 to the 7. Here, by the time I reach 3 cubed, I would already also have covered all of the things that are that are not divisible by 3, mod 3 to the 4. Okay, let me make sure I'm counting this right? So I know that I have 2 times 3 to the 4 things here. I'm saying that there are 2 times 3 cubed possible residues here. No, not 2 times 3 cubed, 2 times 3 squared residues, right? Because it's just 1 or minus 1 mod 9. So 2 out of 9. That means that each of them is going to be just repeated 3 squared times. Okay, so I don't need to be posh and say 3 cubed, right? 27 times each, this one will appear 9 times, and then those are just 1 time each. Okay, let's make sure that I have not messed up. I have a total of 3 to the power of 6. So here, I have 2 times 3 to the power of 5. Here, I have got 2 times 3 squared times 3 squared. So that's 2 times 3 to the 4. And this one, I have got 3 to the 4. Okay, yeah, so that adds up to 3 to the power of 6, which means that essentially I'm imagining that instead of picking x, y, z or a, b, c, I'm picking a cubed, b cubed, and c cubed directly from this pool, except that when I said that 27 times each, they are counted as 27 different copies of this and 9 different copies of these. Okay, so now I need to do the counting. How do I do the counting as easily as possible? Now, I'm looking at this, and clearly, because of the fact that these ones here are not multiples of 3. If I do use this bunch of choices, I need to use 2 of them together. If I do use them. And then the other one is going to just be multiple of 3, either from the first box or the second box. So that, of course, conversely means that from here, I'm using either 1 from these 2 collectively or all 3 from these 2 collectively. Now, it's quite hard for me to describe which 2 I want to pick from here in order that I will be able to pick something from here that works. But I can actually kind of say in the reverse direction. If I pick something from this portion, so if I pick 1 from here, which I know can be done in 3 to the power of 5 ways, Then for down here, anytime when I pick a number, let's say if I pick something that is 1 mod 9, I know that there will be all the 8 mod 9 possibilities that I need in order to make the whole thing sum up to a multiple of 3 to the 7. So that means that since there is 3 to the power of 5, yeah, so it would just be, for this case, 3 to the power of 5 choices. Because every time you pick something on the left column, something on the right column will match it up. For the two of them. So that contributes case number 1. 3 to the 5 times 3 to the 5. Not forgetting it's ordered triples, so I can multiply by 3 factorial. That's case 1. Case number 2 is that I don't use any of these. And if I don't use any of this, then the story basically just repeats, except that now you are cancelling off a 3 cube from everything and asking for divisibility by 3 to the power of 4. Okay, so I will basically just fast forward this, to be honest, because my lesson is coming up in a second, but also because I think we can check through the rest of this to say that if I wanted to, now again, it is that I pick either 2 from here or none from here. If you repeat the same logic, you will again get, for this case, another instance of this 3 to the 5, 3 to the 5 times 3 factorial. Don't forget that you have now 9 times of each, so it's changed a little. Okay, and finally, if let's say that you have to use all of them from here, then you either are going to use the same thing 3 times, or you'll use 1 of each. Because you are just basically now cancelling off 3 to the 6 and you are just getting 3 things that sum to 0 mod 3 from 27 ones, 27 twos, and 27 zeros. So that would be, if they're all the same, this, and if they are all different, then this. Times 3 is choosing the 3 types, right? No arrangement. Once you have 3 cubed, whereas for the other one, there is an arrangement of 3 factorial. Okay, so this whole clumsy mess gives you 5 times 3 to the power of 11, which then is going to evaluate to 735 mod 1000. Now, I'm explaining the general vibe of it, but also you can tell that there will be a lot of checks you would need to do. You would have a lot of things that you may say, are you sure that what you say is correct? This is the challenge of something like question 15 in the AIME. If you were to write it again, you may choose to write it in a more organized fashion. Like let's say, do this inductively. Do it for 3 to the k instead of 3 to the k plus 1. And then some of what I said here as similarly would become a bit of a recurrence or an inductive application. So certainly you could repackage this to look a lot more elegant. But the first time you're solving it, chances are it's going to look more like this. So don't look at the package solution and imagine that that is how the first go at the problem will look. 100% our first go is going to look a lot more like this. Lots of boxes, arrows, and lots of numbers flying all over the place. If you tried to write this in paragraph form, it would easily take you 2 pages. and not be easier to follow at all. Okay, so that brings us to the end of our 2025 AIME 1 paper. Not sure what you thought about it, but I feel that it is a pretty difficult back end, but the front end was relatively achievable. So I would imagine that if you were to do a paper like this, and you are aiming for like 7 or 8 questions, you can safely say that, oh, these are too hard for me or this will take too long, and yet still find that the paper is manageable. So once again, you can look forward to the AIME 2 review coming soon. In the meantime, if you have any questions about this set of problems for the AIME 1, let me know in the comment section below, and also do let me know if there's anything else you'd like me to discuss. Okay, so thank you for watching, bye bye, and see you again soon.